All right, I wanted to send out a video covering a couple of the symmetry group items here. So for starters, this information comes from our book, although it's also found in the notes or similar type information. So this is talking about the different types of permutations we could have for the numbers 1, 2, 3. So it goes through all the different possibilities. The first one is called I for the identity. So identity just means we stay the same, right? We are who we are. That's our identity. So 1 gets mapped to 1, 2 gets mapped to 2, 3 gets mapped to 3, right? So the number on the top says, here's where you started. You started at a 1, and it's going to tell you on the bottom, where did I send that 1 to? So I sent it to itself. We did this, you definitely could see in other parts of the notes something with a triangle. So you start off with here's 1, 2, and 3. So something like, let's say permutation A is going to send a 1, it's going to send it to 2. So it's basically saying, all right, 1, you are now going to land here at 2. 2 is going to go to 3. And 3 is going to go to 1. So that amounts to a rotation of 120 degrees. So we saw these things in terms of R, 120, R 240, things like that. Okay, so the idea though is, at least for a couple of the homework questions, is, well, what happens when we put a couple of these together? So what if we do A and D in that order, right? D and then A might lead us to a different result. So that means we start with A, which says, okay, 1, 2, 3, we're going to send that to 2, 3, 1. And then we're going to say, okay, but also do D. So all of these, notice at the top, start with 1, 2, 3. It's saying, where do you want me to send 1, 2, and 3 to? Where are their destinations? So D says, send those to 3, 2, and 1. So in order to figure out what the final result is, the idea is, okay, we're saying if I do both of these things, where did I ultimately send 1 to? Where did I ultimately send 2 to? And where did I ultimately send 3 to? So let's start with 1. So 1 gets sent to 2. Okay, well, that's just its first change. And then we go over here and we say, okay, if it's at 2, where does it get sent to? Okay, I guess it just stays where it is. So ultimately, I started at 1. I followed it from 1 to 2. I went to the second part of this, which was D. D says, okay, actually 2 can stay where it is. So 1 got sent to 2 at the end of the day. We can do the same thing for the next part. So let me just try to get some of the red out of here, just for clarity. Okay, so let's start with 2. So 2 is initially going to get sent to 3. So then when we look at the second part of this, we start with 3. We say, okay, so 2 is now in the place of 3. 3 is going to get sent to 1. So we use 3 just sort of as a middleman, ultimately, to take 2 over to 1. So 2 is going to get mapped to 1. Now by default, because everything can only live in one place, if 1 went to 2 and 2 went to 1, 3 has to stay itself. But of course you could justify that by walking through where everything is getting mapped. So we could say, okay, I started with 3, it gets mapped to 1. So I'm going to come over here for D and say 1, where does it get mapped? To 3. So ultimately 3 passing through 1 did get mapped back to itself, back to 3. And of course, if you wanted to give this a name, you could look up here and say, okay, well, where do I send 1, 2, 3 to 2, 1, 3? And we would see that here. That's E. So this composition sends us to E. We can do a similar thing with C and E here. So I was just kind of giving us another example of this. So 1, 2, 3, 1, 2, 3, right? These always start with 1, 2, 3 on the top. C says to send this to 1, 3, 2. And E, the one actually we just got, says send this to 2, 1, 3. So we do the same thing, right? We say, well, what happens when I do both of these things? Where is it going to send 1, 2, and 3 to? Well, again, let's just go piece by piece. So 1 stays itself for the first part. So when we come over here, we say, okay, it's still 1, but now we're getting sent to 2. So 1 goes to 2. Then we do the next thing. Let me just use a different color. So 2 gets sent to 3. So I come over here and I say, okay, I'm at 3. Where do you want me to go? All right, I guess you're just staying at 3. So 2 ultimately gets sent to 3. And then finally, 3 gets sent to 2. 2 gets sent to 1. So we're going to go to 1. And of course, that's where we had to go. If we already used 2 and 3, then 1 was the only thing left over. So what's our final result here if we wanted to use one of these names? So 1, 2, 3 gets sent to 2, 3, 1. That looks like A. Okay, so that's the first part of this. Sorry, I should state that, in terms of rotations and things like that, I think the visuals are helpful. There's a couple of those in the book, so I would kind of look through those. But basically, this is just telling you the different types of rotations, or you can, if you have symmetry where you can reflect over a line, that is possible. So that would be something like C. So 1 might stay itself, but 2 and 3 are switching places. Okay. All right, so then there was a question like this in the homework where we've got a set of elements A, B, C, D, and there's an operation. We don't know what this operation is or does, right? This isn't like, we don't know for sure, is it multiplication, addition, division, some other thing. So it's just generically an operation, and it's given by the upside down triangle here. So basically this says, for example, C operated with D is going to say, well, find C in the left column here, and then align it with D in the top row. And basically you say, where do these take you? Jointly, they take you to A. There's your result. So it's telling you how to work in this table under this operation. But it says, hey, find the inverse of each element. Now, what is the inverse? The inverse is going to require the identity. So first find the identity. So that's going to be our first order of business, find the identity element. Okay, what does the identity do? We just talked about this. It is something that sends an element to itself. So we're going to say, all right, is there an element in here that sends A to A? So we're looking for, what would I compose or operate with A to send it to itself? Well, let me go find in this row where A is. Oh, it's right here. So I guess A operated with B got me back to A. So maybe B is our identity element, but let's see if that holds true if I check a couple other elements. So, okay, let me go to the next one. B, let me look in B's row. Oh, yeah, okay, I found B. So what sent it here? What did I have to operate with? B. So B operated with B, gets me back to B. Let's check that this is still true for C and D. So C, well, how did I get back to C? I guess I had to operate it with B. So C operated with B is C. And of course, it would be easy to verify. C operated with D. Oh, sorry, not D. Okay, sorry. Clean that up just a bit. D gets us back to D if I operate it with B. So D operated with B is D. There's actually a faster way to look at this, which is basically like, okay, I started with A, B, C, D right here. Is there a column in here that gets me back to A, B, C, D? It's this one, which means I operated with B. So the identity element is B. All right, so we found our identity element. That's kind of a crucial one. So I'm going to put that over here in red so we don't forget. So if we want to find the inverse of each element, well, the idea of an inverse in general, you might have seen this in algebra or something like that. It depends on the operation, of course. Like, for example, x and negative x are inverses, but they're additive inverses. And that's because if I add them together, so x plus negative x, right, otherwise known as x minus x, I would get 0. And 0 is the identity element under addition, right? If I add 0 to anything, it just stays itself. So basically, that's what happened here. We don't know this operation, this upside down triangle operation, but if I operate with B, every element just goes back to itself. So we had to kind of think about, well, what that looks like. So as far as finding inverses, we're saying, okay, this element and some other element get me back to the inverse. So basically, if we want to find the inverse of A, for example, we're wondering what element I would compose, right, operate with A in order to get to the identity, right? If for additive identity, it was 0. But for us, it is B. So we're basically saying A composed with what gives me B. And so we go, okay, I'm here, I'm A, let me go find B. Okay, what did I have to operate with in order to land on B? Oh, I had to operate with C. So the inverse of A is C, since A operated with C gives me the identity. Let's do the same thing for B. So the inverse of B is blank, right? Basically, we're saying B operated with or composed with something has to get me back to the identity element, right, which is B. So what do I compose with B to get B? Okay, I guess B. A lot of B going on here. And I'll clear out the table so we can maybe look at the next one again in the table. The inverse of C. So this is C operated with what gets me back to the identity, gets me back to B. So C, I find the result, the end result in the white portion of the table here. How do I get to B? Well, I have to compose it with A. So the inverse of C is A. And this tends to be the case where if you compose something, right, if A is the inverse of C, C should be the inverse of A. That's generally the case. All right. And then we would say, okay, well, that kind of leaves D to be the inverse of itself just by deduction here. But we could say, well, let's look for where we land on B. Oh yeah, that's D right there. And that's about it.